In this video, we're going to talk about two more tests for determining divergence and convergence. They are called the divergence and integral tests. So the first one, the divergence test, is also called the Nth Term Test, and this is the one that you should always try first because it's one of the easiest ones to do. Alright, so all it says is that if you have this series where A sub n is your formula, your general formula here, then if you take the limit of that general term and it doesn't equal 0, then the series has to diverge. But you have to be careful because if it does equal 0, then that doesn't tell us anything. It could diverge or it could converge, and we don't really know, so we need to do another test. So just be careful. If it equals 0, then that means it doesn't tell us anything. But if it doesn't equal 0, then we know for a fact that it diverges. Alright, so here are a few examples that use the nth term test to determine if the series diverges. Normally, you don't just have to do the nth term test, because if it equals 0, then you have to go on and use another test, but we'll see examples of that later on in a different video. Okay, so here's an example. We use the nth term test to determine if the series diverges. So in problem A, we have the series from n to infinity of 1 over n. And 1 over n is our a sub n, so that's what I want to take the limit of, whatever's after the summation, basically. And n is going to infinity because our series was going to infinity. So the limit as n approaches infinity of 1 over n, you can think about, basically if you plugged in infinity, you have 1 over something really huge, which is equal to 0. So that's inconclusive. I don't know if this series diverges or converges. I don't have enough information. If you remember from the previous video, this is actually the harmonic series. So this one I know, not because of this test, but I know in other ways that the harmonic series diverges. So it's equal to 0, but it doesn't tell me anything, so then that's why I had to use my knowledge and say, okay, harmonic, so it must diverge. But for right now, all we need to know is that this is inconclusive because it equals 0. Alright, so my next series that they give me is 3 times n to the 5th over n plus 1. It's still an infinite series. So I take this part right here, this is my general term, and I take the limit of that. So the limit of 3n to the 5th over n plus 1. We're going to infinity, which means that I can ignore the plus 1 because infinity plus 1 is very, like, the plus 1 doesn't matter. So really I have 3n to the 5th over n, and then I can cancel this n with one of the n's up here, so really I have 3n to the 4th. And if I plug in infinity, now this is going to infinity, which, according to my test, it does not equal 0, so this series diverges, and then I'm done. I don't have to do anything else. I don't have to see if it's a p-series or a geometric or do anything else. I am finished, because I already know it diverges. And then for C, I have another infinite series, 0 to infinity of 1/2 to the n. So this is my general term. I'm going to take the limit of that. You have to be careful with this one because 1 to the n, well, you'll see. We need to distribute that n to both of the things. So I have 1 to the n, but 1 to any power is just going to be 1, so really 1 to the n is the same thing as 1. And then 2 to the n, on the bottom, right, 2 to the n. Okay, so n is approaching infinity, but I have 1 on the top, and then 2 to the infinity on the bottom, so really this is 1 over something huge, which is 0. So according to my nth term test, this is inconclusive. So I need to do something else. And this, I know, is a geometric series, so I could go on and say, alright, well, this is geometric series r is equal to 1/2, and 1/2 is less than 1, so that means that this series converges. So I had one that was equal to 0 and diverged, and this one's equal to 0 and it converges, which means equal to 0 tells me nothing. But if it's not equal to 0, then I know for a fact it diverges. So here's one for you to try. Use the nth term test to determine if it diverges. You don't have to do anything beyond that, just do the nth term test and see what happens. So pause the video here, try this, and then we'll look at the solution for it. Alright, so here we have, this is my series, it's an infinite series, this is my general term, so I'm going to take the limit of this term. As n approaches infinity, 1 over n goes to 0, so really I have 1 plus 0, which is just 1. And then my n on the outside stays n, but n 1 to the any power is just 1, so really this limit is equal to 1. and 1 does not equal 0, so that means that this series diverges. Alright, so that's the divergence test. The second test that we're looking at today is called the integral test. The integral test, it's a little bit more work than the divergence test, but it's also kind of a general purpose one as long as our function meets the qualifications. So we have this series here, it's just any general series, and so our general term is a sub n. What we're going to do is take that and turn it into a function. You can make this f of x if you want to, or leave it f of n, or f of y, or whatever letter you feel like using. But when we turn it into a function, then we need that function to be positive, continuous, and decreasing. For, in this case, it would be from 1 to infinity. So it has to be on whatever interval we're looking at here. And we'll see that in the example that's coming up. If f of n meets all of those qualifications, then that means that this series and this integral do the same thing. So they either both converge or they both diverge. So if you can figure out what the integral does, then it tells you what the series does. And usually it's easier to figure out the integral than it is to figure out the series. Alright, so here's an example. We're going to use the integral test to determine if the series, this one, converges or diverges. So again, this is the harmonic series, but it's a really easy one to use, so that's why we're using it for this example. We're going from 1 to infinity. My a sub n is 1 over n, so I'm going to change that into a function. Now it's f of n is 1 over n, or you could say f of x is 1 over x, whatever you like better. Now if I graph this as a continuous function, I get a graph that looks like this. So it's positive on 1 to n, or 1 to infinity. It's also continuous, because I can draw that without lifting my pencil, on 1 to infinity. And it's decreasing because it's continuously going down. So every time I plug in a number, like the next number over, it's lower than the number before it. So like f of 3 is less than f of 2, and f of 4 is less than f of 3, and so on. And that's true for everything that I plug in. Alright, so all three of those are true, which means I can use the integral test. So basically, I'm just taking the integral, and then my series was 1 over n, so that's my integrand now, and then dn, so that I can take the integral. This is an improper integral, so I need to bring that infinity out of the bound and put it as a limit in front. So it's the limit as b approaches infinity of our integral from 1 to b of 1 over n dn. And I know the integral of 1 over n dn is natural log of n from 1 to b, where b is approaching infinity. And then I plug in b and 1, so natural log of b minus natural log of 1 as b goes to infinity. And the nice thing is that the natural log of 1 is 0, so that just goes away. And now I have the natural log of b as b is approaching infinity. And if you remember what natural log looks like, it kind of goes up, but it keeps increasing. So as we go towards infinity with our b, natural log also goes towards infinity. So that means this series diverges. And like I said, this was the harmonic series, which I know the harmonic series diverges, but now we have proof that it diverges because now we've done the integral test on it. Alright, so here is another note that might be important. It's not a huge thing, but just so you're aware, if the integral and the series converge, they don't necessarily have to converge to the same value. It's totally fine. All we care about is that they converge. It doesn't matter if one converges to 3 and one converges to like 1.5. It's fine. We just want to know that they converge. But that also means that if the integral converges to 2, you can't assume that 2 is also the sum of the series. So that's important to remember. Alright, here is one for you to try. Use the integral test to determine if the series of 1 over n square root of n converges or diverges. Pause the video here, and then we will look at the solution. Okay, so here's my series. The very first thing I need to do, I'm going to take my general term. Actually, the very first thing that I would really do is I would do the nth term test on this to see if it converges or diverges. In my mind, real quick, I can take the limit of this, and I know that that's going to equal 0, which is inconclusive, and so I have to do the integral test. But they told me in the instructions to do the integral test anyways. So, anyway, we change our general term to a function. So the function of 1 over n root n, and it looks like this when I graph it, which means, oh, and I can also simplify this, so really I have 1 over n to the 3 halves. Looking at my graph, I can tell that it's positive, decreasing, and continuous on this interval, 1 to infinity, because I went from 1 to infinity with my series. So that's where these endpoints are coming from. Because it is all 3 of these things, then I can do my integral down here. So my integral of my function, I just rewrote this as n to the negative 3 halves. It's an improper integral, so the infinity has to come down and turn into a limit, and then that bound has to turn into a b. Alright, so we're going to do the integral of n to the negative 3 halves, which gives me negative 2n to the negative 1 half from 1 to b as b approaches infinity. And then if I plug in my bounds here, I get negative 2 over root b, which is sort of a simplification of this. And then if I plug in 1, I get negative 2 over square root of 1, which is just 1. So this one, as b goes towards infinity, the square root of b also goes towards infinity, which means I have negative 2 over infinity, which is really just 0. So I have 0 minus a negative 2, or 0 plus 2, which is just 2. And because the integral is equal to something that's not infinity, because it's equal to an actual number, that means that my integral converges, which means that my series also converges. And another way I can check that, this is a p series because I have 1 over n raised to the p, and p is 3 halves, which is greater than 1, so that means that it has to converge by the p series test as well. Alright, so here's a summary so far of what we've learned. In the last video we talked about a geometric series that looks like this. We have a times r to the n. It converges if the absolute value of r is less than 1, diverges if the absolute value of r is greater than or equal to 1. P series looks like this, 1 over n to the p, converges if p is greater than 1, or diverges if p is less than or equal to 1. Nth term was the first one we learned today, so any series, we can do this for any series, and it should be the first test that you do, because it's the easiest one. If the limit is not equal to 0, then it diverges. If it does equal 0, then it's inconclusive, and we have to do another test. And then we just finished talking about the integral test, which you can do for any series as long as the function is positive, decreasing, and continuous. If the integral converges, then the series converges, and if the integral diverges, then the series diverges. So those are the 4 tests we know now. In the next video, we're going to learn another test, and then we will update this chart. So that's it for now. Make sure you ask questions if you have them.